Oh, good morning. In this lecture video, I'm going to explain multiplication and division instructions of microcontroller. So, as we observed in the previous videos, addition instructions and subtraction instructions. Okay? So, in this video, I'm going to explain multiplication and division instructions. So we know the process of multiplication and division. So this is the process of multiplication. So if we multiply two numbers, one number is called as multiplicand, another number is called as multiplier, and this is the operation, and you will get a product. Okay, this is the general procedure. So and division process. So these are the parts of a division. So we have a divisor. So if you want to divide 11 by 2 means 11 is the dividend, 2 is the divisor. You will get a quotient 5 and remainder 1. So result of division is quotient and remainder. Operands are dividend and divisor. Here multiplication operands are multiplicand and multiplier. Result is product. Result is product. Okay. So 8051 performs 8-bit integer multiplication and division using register A and B. As I said, no, B has a specific register application, that is it holds one operand of multiplication and division. That is, it performs in integer. It won't consider fraction. As if you consider fraction, so 11 by 2 you will get a 5.5, but that is a 5.5 is a fractional, that won't be there. So it gives the result as quotient 5 and remainder 1, that is called integer operation. Okay. And register A holds 1 byte of data before the operation and 1 byte of data after the operation. That means in the multiplication also it holds low byte of result. In division it holds quotient after the operation. Again, B register holds 1 byte operation before the operation and 1 byte after the operation. After the division operation, B register holds a remainder and treats the numbers A and B are unsigned, and programmer must devise a ways to handle the signed numbers. Okay. Now first we'll see multiplication. That means unsigned number in A is multiplied by unsigned number in B. So the instruction format is mul AB, multiply A by B, store low order byte of product in A and high order byte of product in B. That means after the multiplication, A will be having a low byte of result and B will be having high byte of result. And here overflow is set to 1 if the result of A into B is greater than FF. It doesn't mean an error. It indicates result is more than 1 byte and I byte is present in B register. Indicates result is larger than 8 bits and I order byte of result is present in B register, and carry flag is always a 0. So we know the largest possible product, if we consider both the operands are FF, you will get a result FE01. So when both A and B is equal to FF, so A will be having low byte result as 01 and B stores the high byte result FE after the multiplication. Again here overflow is set to 1, indicates B having high byte of result. Okay. This is what the operation. Okay. And in case of multiplication, again this is also uses registers A and B as both source and destination addresses. So unsigned number in A is divided by unsigned number in B. That means A will be having a dividend and B will be having a divisor. So unsigned quotient will be stored in A register and unsigned number as a remainder will be stored in B register after the division operation. So C is always a reset. If it is, overflow is set to 1 if you try to divide the number by 0. Shows division by 0. So the instruction format is DIV AB. Divide A by B. Store integer part of quotient in A and integer part of remainder in B. Okay. That means division always results integer quotient and integer reminders. So this means this is the operation. A having dividend, B having divisor. So A by B After result, A will be having integer quotient and B will be having a remainder. Okay. If you consider an example, 213 divided by 17 in decimal, you are expecting the quotient 12 and remainder 9. So as we know the formula to obtain the remainder, dividend is equal to quotient into divisor plus a remainder. So remainder is equal to dividend minus quotient into a divisor. In such a case, 213 remainder is equal to 213 minus 12 into 17. 12 is the quotient, 17 is the divisor. So that is equal to 9. So this is how we obtain the remainder. Okay, that means in hexadecimal, 213 means it is a D5H, 17 means 1H. So after the operation, quotient here it is told now, that means 0C quotient and 09 remainder. Is it clear now? So this is about division and multiplication instructions. So now we'll see third set of fourth set of arithmetic instruction, that is incrementing and decrementing. Okay. So it is a simple arithmetic operation. That means incrementing means adding 1, decrementing means subtracting 1 to the number, adding 1 or subtracting 1 from the number. So it is very useful operation when coupled with a repeated operation. That means if you want to repeat some set of operations, it is most useful. That means to increment or decrement until a desired result is reached. So we observe that the decrement jump not zero instruction. So there we decrement the content of R2 and we repeat until it is a 0. So to repeat a couple of operations, this is most important. Either to increment or decrement until the desired result is reached. So again we have two instructions are available, one for incrementing and for decrementing. The general format is increment destination. So that means destination will be replaced with the destination plus 1. That means it acts as both source and destination. Finally result will be stored, that is why we specify it as a destination. And similarly for decrement operation, DEC destination. So destination is equal to destination minus 1. So again here destination can be a register accumulator, register RN, a direct or indirect addresses. So let's see the different mnemonics. Different mnemonics for increment is increment A. That means A is replaced with A plus 1. And increment Rn, Rn is replaced with Rn plus 1. Increment at Rp means content of Rp, content of the address in Rp is replaced with the content of address in Rp plus 1. And increment direct address, increment DPTR. And for decrement operations, decrement A, decrement Rn, decrement at Rp, decrement address, but we doesn't have decrement DPTR in correspondence to increment DPTR. So then what we can do for decrement operation? We need, as we know, so DPTR can be used as a DPL and DPH. So first we decrement DPL. So when it reaches 0, then we decrement DPH. Even though if at all if you want, we doesn't have decrement DPTR as in case of increment DPTR. And here we should observe what all the flags are affected. So match flags are not affected. No flags are affected. So if 8-bit contains overflow, 8-bit contains overflow from FF to 00. That means if we keep increment the 8-bit number, it increments up to FF. That is the maximum. That is the maximum. Then it becomes, again if you add 1 to the FFH, there as if carry occurs, but carry flag will not set. Result is 0 0. Increment means adding 1, no? We keep on adding 1, and when we reach to FF, if we add 1 to FF, you will get 1 carry and 0 0. So 0 0 will be the result. Carry flag will not be affected as in case of addition instructions. That is why we said math flags are not affected. So we say When it reaches to maximum, then it becomes a 0. That is called overflow from 0 ff to 00h. And similarly, in case of decrementing, we keep on decrementing, and we reaches 0 0. Again, if you subtract 1, so we need a borrow and result is ff. So borrow is not set, so result becomes ff. So this is called as underflows from 00 to ffh. And in case of 16-bit number, that is dptr, we keep on incrementing. When it reaches ffh, again still if you increment, it becomes a 0 0. And we don't have decrement dptr instruction to match increment dptr instructions. Clear now? So this is about arithmetic instructions. So all the arithmetic instructions are over. So in the next video, I'll explain the logical instructions. Thank you.